Hello everyone, my name is Professor Andrew Ellis and I want to tell you just a little bit about my research. And my research is a really nice illustration of the great diversity of chemistry. We look at chemical phenomena. We're interested in particular in how molecules interact with each other, but we do so in an environment which is very unusual, very much a physics-like environment, and that is superfluid helium. So essentially we trap molecules or we grow things inside this superfluid helium environment. And one of the things that does is provide a very, very cold environment in which to look at molecules. And I'll tell you why that's useful in just a moment. To make superfluid helium, you really have to cool helium down to a very, very low temperature. Now, to actually liquefy helium, you have to get down to something like 5 Kelvin, and that actually only makes what's known as the normal phase of helium, the normal phase of liquid helium. And to actually get to the superfluid phase, you have to cool down to around about 2 Kelvin. And once you get down to 2 Kelvin, you get into this superfluid phase, you have a liquid which is extremely weird. And one of its properties is that it has zero viscosity. So things can move through this liquid with essentially no friction. Now that's quite a useful property for us, but it's not a critical property for us. The main property for us is that it provides an environment in which to trap molecules and then to explore how they behave at very low temperatures. But if we try to put those molecules into that cup of superfluid helium that you can see in this picture, it wouldn't work. And it wouldn't work because the molecules would very quickly gather at the walls. And that's because helium is a really terrible solvent, and molecules don't like to stay inside that helium if they can possibly avoid it. And we need to find a way around that. The way we get around that is that we trap our molecules inside droplets of superfluid helium. And this is a cartoon which illustrates how that works. So on the left-hand side, you can see that bundle of blue dots there, which is meant to indicate a helium droplet. Now, this helium droplet is very, very cold. It's typically around about 0.4 Kelvin, so just 0.4 degrees above absolute zero of temperature. Now we can add molecules to those droplets, and I try to show one being added in the middle part of the cartoon there with that red dot in the top right-hand side. That atom or molecule, when it gets added, has some excess energy, and when it hits the droplet, it causes some helium atoms to fly off because they're very weakly bound. And then what we get on the right-hand side is a very, very cold atom or molecule embedded inside the helium droplet. We could then go on. Here you can see that we've added a second atom or molecule of the same type. It comes in, it will go inside the droplet, and it'll eventually find the other atom or molecule, and they can stick together, or so-called dimerize. And when they do that, that will also release some energy, and some more helium atoms will fly off, and we're left with that dimer at very, very low temperatures. Now, the nice thing about low temperature, there are many useful things about working at low temperature, but one of the things that it does is, for example, if we want to look at those molecules or that dimer via spectroscopy, it simplifies the spectrum. The low temperature simplifies the spectrum. And there are other useful things about working at low temperature, which I don't have time to go into, but there are many, many useful properties that come out of this. So we can add atoms and molecules to these droplets, and essentially we have a beam of these droplets in our experiment, a so-called molecular beam. It's like an aerosol, if you like, a spray of these droplets, and we can then add molecules or atoms to those. This slide shows one of the experiments that we have in our lab. We have several helium droplet systems, and these experiments really involve homemade equipment, if you like. We have to build the apparatus mostly ourselves, and that's what you can see on the right-hand side of this picture. So what you can actually see are a bunch of vacuum chambers. Some of them are shrouded in aluminium foil. You can also see a whole bunch of pumps there which are evacuating those chambers. And if you look at the very far end of the system, where there's the last, in roughly the center of the picture, where there is an item enveloped in aluminium foil, that's actually a mass spectrometer. So what's happening is the helium droplets are made on the right-hand side of the picture, and they flow along towards the center there through those vacuum chambers with the aluminium foil on, and eventually you get to the mass spectrometer at the end there, which is an important part of our experiment. On the left-hand side, you can see that there's actually a laser there. In fact, it's a tunable high-power infrared laser system, and that generates a beam of intense laser light that actually goes, essentially turns to the right, and you can see a tube connecting the laser on the left-hand side to the apparatus on the right-hand side, and that laser beam goes through that tube, turns right again, and counterpropagates against the direction of the molecular beam. And that's used to do spectroscopy of atoms and molecules inside the helium droplets. So that's, broadly speaking, what our experiment actually looks like. So here is an example of what we can do with that apparatus. In fact, if I bring up everything on this particular slide here, what you can see at the top there is a reaction shown here, which is actually an ionization reaction. So what we have there is a dimer of acetic acid, so two acetic acid molecules stuck together, if you like, and they're exposed to electrons, which can knock an electron out of the dimer. And what it's done, if you follow the reaction from left to right, is it hasn't just ionized the molecules, it's also fragmented part of it as well. So you lose CH3COO, and you're left behind with a protonated acetic acid molecule or molecular ion. Now, what we're interested in doing with this is actually trying to look at the spectroscopy of that ion and the infrared spectroscopy of the ion, but we can't use standard infrared techniques to do that. They're just not going to work. They do not have the sensitivity. So the way we're going to do this, the way we have done this, is that we actually note that when we ionize those acetic acid dimers, we also have some ions which come out of the droplets with helium atoms attached. And they're essentially shown in the reaction at the bottom there, the bottom left-hand side. And if we send infrared radiation in to encounter those helium-doped ions, if the wavelength is right for absorption by the protonated acetic acid, energy will go into that ion, and that excess energy will then evaporate off helium atoms. And so this gives us a means of recording the infrared spectrum of the ion. And we can do that by simply looking at the signal of those helium-doped molecular ions, and then just watching how that signal disappears as we scan the wavelength of the infrared radiation. This is a very unusual way of recording an infrared spectrum, sometimes called a photodissociation spectrum. Sometimes it's also called a messenger spectrum as well, because the helium is essentially acting like a messenger, telling us when absorption of the infrared radiation has taken place. On this slide, it kind of shows you why we want to do that, because we're interested in this from the point of view of some basic organic chemistry. If you look up the reaction that one uses to form esters, you normally see a reaction between an alcohol and a carboxylic acid. And the starting point for that reaction is very often, or the assumed starting point is that an acid has to be added, a strong acid such as sulfuric acid is added to protonate that carboxylic acid, in this case acetic acid. And you can see in the middle of the screen there the assumption that that proton has gone onto the carbonyl group there. But actually, nobody's ever seen that particular reaction intermediate. And we wanted to try and see if we could see that in our unusual environment, the helium droplet. Next, This slide here is a rather complicated looking slide, so we don't need to go through this in any detail. But what this slide shows at the top is the infrared, or one of the infrared spectra that we've actually recorded. And then below that you can see two other panels which have color schemes in them, which actually show us predictions from essentially from quantum chemistry, some calculations. And these allow us to actually say what is going on inside these helium droplets. And effectively, to cut a long story short, the big peaks in the spectrum correspond to protonation of the acetic acid at the carbon. And if you look at the structures in the top right there are three different conformers, three different arrangements or possible orientations of the OH groups there. And we're seeing the one on the left-hand side. It's called the EZ conformer. But actually, if you go to the middle panel, you can also see a structure shown there. And this actually arises from protonation at the OH on the acetic acid. So we can also see that species as well. And that's quite an interesting species because there's some controversy about actually which of these ions is actually involved in the mechanism for forming esters. And we can actually now see both of those things. So this is an important piece of information in trying to understand the mechanism for formation of esters by acid catalysis. And we published this work last year. There are many other things that we can do with liquid helium droplets. And let me close by just showing you one other thing, which is very, very exciting. And that is, instead of trying to grow small collections of atoms or molecules, maybe we want to grow something a bit larger, maybe with hundreds or thousands of atoms or molecules, particularly sort of particles, nanoparticles. And we also want to take them out of the helium droplet. So how can we do that? Well, you can see this cartoon here, and on the left-hand side, you can see a helium droplet with such a particle grown inside. And we can get that particle outside of that helium droplet just by letting the droplet smash into a solid surface. The helium will then all evaporate away, and what we're left with is a particle attached to that surface. And then we can go and look at it with other techniques such as microscopy, and I'll show you in just a moment on the next slide what that might look like. But the reason why we want to do this is because helium droplets allow us to make many unique objects that are not possible to make using conventional wet chemistry methods. And for example, we have managed to make new types of nanoparticles with extreme magnetic properties by using this technique. And this is a very, very exciting application of our method. This slide actually shows one of those TEM images. So TEM stands for transmission electron microscopy. So it's a very high resolution form of microscopy. And this particular image actually shows a silicon-coated nickel nanoparticle. So that dark region in the image is actually a nickel nanoparticle, and you can see there's a much lower contrast. You can see a thin shell around that nickel nanoparticle, which is the silicon. And at the bottom left there, you can actually see a scale marker. So 10 nanometers is the length of that line, and so that particle is around about 30 to 40 nanometers in diameter. And we can play around in our experiments with the size of those particles. In fact, we can even grow wires in these experiments. We can change the elemental composition. We can grow extra shells. It's an extremely flexible and exciting way to do nanoscience. And it's one of the exciting things that we're actually doing. So what I've hopefully done in my short presentation here is just give you a flavor of the type of experiments that we work on. And hopefully I'm enabling you to see that chemistry is an incredibly diverse area. We happen to be working at the physics end of the subject, but of course chemistry is much bigger and broader than that.